Hi and welcome to video 2 of my graph theory video series. This is video 2 of 7. We're going to talk about the adjacency matrix. So an adjacency matrix is a matrix representation that tells you which edges are connected to which edges. Now you'll recognize this graph. I've used it a few times. It has 5 vertices and therefore our matrix is a 5 by 5 matrix. And it's telling us the connection between A, B, C, D and E and A, B, C, D and E. So we don't usually put that detail in it, but that's the understanding that we have. If there wasn't an obvious order, if it wasn't A, B, C, D and E in an obvious order, then you might have to give some direction as to what the order is. And as you can see from this, the zeros tell you that A is not connected to anything, which is what we've got. B on the other hand is connected to C and D twice. So B is connected to C once and D twice. And as you can see down here, B is connected to C once and D twice. So we get that symmetry because this is an undirected graph. So a connection from B to C is also a connection from C to B. C is connected to B once and D once. Let's check. It's got 2 connections and there it is. D is connected to B, C and E, but twice to B. So it's got 4 connections. 2 to B, 1 to C, 1 to E. You can confirm that. And E's got an interesting one. It's connected to D, as you can see here. It's also connected to itself, as you can see here. Now, technically, and this is a very context-driven thing, E has degree, so degree of E is 3. Technically, because it has 3 things coming in and out of it, but it's also connected by only 2 edges, so it's kind of 2 as well. And that depends a little bit, well, the context drives our understanding of that. When we get to something called Euler's formula, and the degree of a vertex actually becomes important, or not Euler's formula, sorry, Eulerian graphs, then 3 will be the important number. So we say degree E is 3 because it's got 1, 2, 3 things coming in and out of it, and so that gives us our 3. But you'll notice here that if you add up the numbers in here, because that's only 1 edge between E and E, we only get 2. So we have a situation where, because we typically put a 1 in the adjacency matrix, we don't quite get it leveling out, and we've got to deal with that sometimes. So moving on, here's my summary. A to B, A is connected to B, then we place a 1 in the row A, column B, and a 1 in the row B, column A. If A is connected to B in a directed matrix, graph, sorry, then we put a 1 in row A, column B only. So for the directed matrix, then we put a 1 here, we don't put a 1 there. So this is A connects to B, but B does not connect to A. So we always go from that column first, and that explains the connection point. Let's have a look at an example. Determine the adjacency matrix for this one. So again, I'm going to do a 6 by 6. So, and what I'm going to do, which I think is quite clever, don't put your bracket out yet. You might feel like you want to, but just sit there and pretend it's like a table. So I've got 1, and I've got 1, 2, 3, 4, 5, 6, and 1 connects to 2 twice. It connects to 5. Oh, sorry, it connects to 5 twice. So I can see 2 and 2, and now I'm going to have a look at number 2. 2 connects to 1 twice, and it connects to 4 once. And now I'm going to have a look at number 3. 3 connects to 5 once, and that's it. I'm going to have a look at number 4. 4 connects to 2, and it connects to 5 and 6. There are no loops here, so I'm expecting my diagonal will have zeros. 5 connects to 1 twice. It connects to 3 once, it connects to 4 once, and it connects to 6 once. And it's got 5, so that works. 6 connects to 5 and 4. So 5 and 4, and I've written a 6 here, I see. You're probably sitting there talking about that behind the video, so I apologize about that. Now I can add the matrix bit. I could even be a bit cheeky now I've set it up and rub out the numbers. And then I just fill in the rest with zeros. 0, 0, 0, 0, 0, 0, 3. What did 3 connect to? Because I'm going to do a whole bunch of zeros. 5. I've connected 5 to 4, 6, 1 twice. Oh, and 2. I've marked that up too. 5 doesn't connect to 2, so that's a 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Whose idea was, oh, that shouldn't be a 4, that should be a 1. So you say numbers and then I write them down. And there's my 1s and 0s. There are 2s where there are double connections. So you can see that matching out. And we also get this diagonal of, oh, 6 doesn't connect to itself. I've really not done well here. There we go. We get this nice diagonal of zeros. So 6 connects to 5 and 4. There should have been 1 there and there. And because we're not talking about a directed matrix, we've got a symmetry here. So the symmetry means that we've got 2 and 2. 2 and 2 there. 1 and 1. Symmetry across that yellow line. 1 and 1. 1 and 1. 1 and 1. 1 and 1. There's our symmetry. Now let's draw a graph for the following matrix. I've got 5 vertices, so we'll have 1, 2, 3, 4, 5, and vertex 1 connects to vertex 2 twice, connects to vertex 3 once, and it connects to vertex 5 once. Vertex 2 connects to vertex 1 twice, which I've already done, so I can tick these off as I go. And it connects to vertex 4 twice. That's vertex 3. So 4 twice will be, what I might actually do is I might swap this so it's 1, 2, 3, and then I make this 4 and this 5, because 4 is associated to 2 and 5 is associated to 1. So then I can put that there, and then I can do this. We'll talk about planar graphs later, and you'll see that this is an important process. Also connects to 5 once, so I might just do that for 5. That's that. 3 connects to 1 once, we've got that. 3 connects to itself. There we go. And then 3 connects to 5 once. And then we've got 4 connects to 2 twice, connects to 5 once. And then we've got 5 connects to each of them once, which we should have already because we've set all the others up and it's worked. So there we go. You may have done that. You may have drawn it completely differently. What about this one? Can we draw this? The question is, what has changed? So if I have a look here, see that this is same. That's missing and that's missing, but that's still there. So now 2 is not connected to 4 anymore, and 2 is not connected to 1 anymore. But 2 is connected to 1 here. So this must be a directed graph because there's no symmetry across the line. So that means that this connection must be directed, which means that all of 1's connections must be directed. So I've written down here, and I'll finish the graph in a second, but you won't have to face tricks like that in your exam. But the idea here is to get you thinking about things. Ultimately in your exam, you'll be dealing with, pretty straightforward, we'll tell you it's a directed or undirected. But definitely play around with these and look for evidence for directedness or undirectedness and what you see in those cases. But 2 is only connected to 5, so we draw a little arrow there. And then if we keep on going, 3 is connected to 1, but we've already used that one up, so I better do that. 3 is connected to itself, so I can just pop an arrow there, that's fine. And 3 is connected to 5, so there's an arrow there. 4 is connected to 2 twice, so these connections I shouldn't have rubbed out, but it just means the arrows go like this. And 4 is connected to 5 once, so we'll take that. And 5 is connected to everything once, but I've done arrows in the opposite way, so I better put another one back. So we've got arrows in the right direction for each of them. And when it's directed, you get a little bit more complicated the graph there, but that graph still works. Anyway, this exercise was more about the adjacency representation of the graph. So example 1, the first one we did, is probably a little bit more important, being able to do that. So can you read and interpret an adjacency matrix? Can you draw a graph simple or directed from an adjacency matrix, and vice versa? All the best.